All right, people, we've started. Thanks for coming today. First things first, I need to make sure that everyone is able to watch the video on demand system. I mean, do you all have access to the video on demand system, right? And you should have noticed normally if you're keeping track of what's going on in the embedded system course, I've uploaded, on a weekly basis, I upload the face-to-face lecture as PowerPoint slides, PDF slides, and at the same time I upload the video of the video on demand. Who amongst you, by show of hands, have already seen last week's face-to-face lecture? All right, so the majority, I hope. Please do note that in order to have a logical flow and to understand what's going on whenever you have a face-to-face lecture with me, you need to have the prerequisite, which is last week's lecture. So if I'm not mistaken, you guys are the even number or the odd number? I'm never sure. The even number. All right. So I'm seeing you twice this week, and I'll be seeing you not next week, but the one afterwards. Correct? All right. So what I've keep it down to the minimum, please. So what I showed last week on the face-to-face lecture is an Arduino board, and those who've seen the VOD already know how to place the different components on a board. So from now on, one of the things that you're learning with me in this particular course is you're not going to call the whole board a microcontroller, and it's definitely not named Arduino. Well, this board in particular is called Arduino Uno, and this is a whole board, and it has a couple of microcontrollers. And I'm saying a couple of microcontrollers because there's more than one. Who amongst the people who watched the video or seen the lectures are able to place correctly, to point out correctly the microcontrollers, also known as MCUs, on this particular board? Go ahead. You need to really speak up because there's the mask, the old age and everything. Oh, first off, you need to tell me what the clock is, so it's not that obvious. All right, so what you're seeing here is actually called an external clock. Shh, keep it down, girls, please. This is called an external clock, and here we have one microcontroller, and then we have another one, the biggest one. Who amongst those two is the main one? The one that you get to program is the big one. All right? This one, the Atmega 16 here, is actually a microcontroller, and you can take note of that, that is strictly used to control the USB and the communication that happen with the board. It's less expensive for the people to use this particular microcontroller with a dedicated task instead of using a different module that costs a lot more money. Normally, you're not supposed to access and use this microcontroller unless you're a hacker, and I strongly suggest that don't become hackers. Wait until the end of the course. All right. The main one that you use is definitely this one, this Atmega here. And we're going to find out today, in today's lecture, the different suffix, because it's another Atmega microcontroller here. However, it doesn't have the same suffix. Anyone can guess what the 16 stand for? Come again? One more time. Fours? Cores? Definitely not. A microcontroller is, I will most probably bits, but we're going to see that it has a particular meaning. We're going to find out today. What, do you have a suggestion? Come again? Clock? Not really. But nice try, because 16, it looks like the 16 megahertz here. So on. All right. So throughout the course, we're going to learn how to interpret and we get the design and differentiate the different modules that are that we're going to use. All right. In last week's lecture, I wanted people to pay attention to a particular pin here. That being said, one of the key things that you needed to go, shh, hey, you're late, so keep it down. One of the key messages that you needed to go home with last week, or you were already at home, so you needed to learn, is that usually a microcontroller, all the time, a microcontroller contains a processing unit, but also contains a memory unit and some I/O modules. Why the I/O modules are important? To be able to communicate with the outside world, whatever the outside world is. All right. So we have a bunch of ins and outs, and here you can notice the legs. Some of the legs of the die here of the chip are actually pins that are used to communicate with the outside world. All right. To get stuff from outside or to spit out stuff from outside, etc., etc. What you need to learn today is those legs here are physically connected throughout the board to the different pins here. All right? So one of the pins that are present in the microcontroller here, one of the pins that are connected physically to the microcontroller is called an ARAF. Now I'm calling for your intuition as future engineers. ARAF, does it ring any bell? Does it? Huh? All right. So your friend here is, I don't want to talk about voltages for now, but because we've covered voltages last week, but in ARAF, you can read ref. Most probably in the context of electronic components, etc., a ref should be some kind of reference, all right? And A, in electronics, it's not digital, it's more analog. So the A could be analog. This is just an intuition. I'm not expecting you to know that, but you're going to learn it today, inter alia. So I'm going to focus on this particular thing, and throughout this example, we're going to learn what are the different pins and what are the different slots that could be useful in different microcontrollers and different boards. All right, so I'm using this as an example, but you can generalize this particular approach. All right, let's go for it. Who am I looking at? Guy in orange. All right, so again, now you have some basic knowledge using the 2 lectures till now. So most probably you can name the different things that are here in that particular system. All right? Most probably, I said, not definitely. So let's go and shoot for the different things that you are able to see. So what do you see? What is the first thing that strikes you? Come again? Power supply. Awesome. So most probably the power supply is here to do what? To give some voltage to the different components that are present in my system. So let's go for the different components that are here. So skip this one for the time being, and you should be able this week, you should be able to name that particular component here, because we've seen it in last week, in the last lecture. You don't know. Who can help them out? MCU? Yeah? Microcontroller, definitely. So one of the things that we've learned last week is an MCU is a microcontroller unit. All right? And by definition, a microcontroller contains what? Just a CPU? It contains a bunch of stuff. Mainly a memory and some IOs. Mainly. And it has some other things as well. Unlike a processor is only a CPU. Guy with glasses. Still your turn. Tu bist dran. Okay, so it's connected to what? To a temperature sensor. All right, so normally what do I use a temperature sensor for? That's awesome. You got it right. What do I use it for? Measure the temperature. Is the temperature an analog element that I measure or is it a digital one? An analog one. Perfect. Have you taken DSD with me? So in order to travel from the analog word to translate it into the digital one, what do I use? A converter, an ADC, an analog to digital converter. Everyone is on the same page? We all good? All right. So here's my temperature sensor connected to the MCU, and I should have outside or inside the MCU some kind of converter. It's a trick question, but I mean, come on, I'll take any answer. So my ADC that allows me to go from analog to digital, should it be inside the microcontroller or outside? I don't really care as long as it's there. All right. So if it could be the sensor itself, it has it inside it, right? It could be somewhere here in between the connection, or it could be inside the MCU. And we're gonna find out that most probably you're gonna find something inside the MCU. It's easier for everyone. And there's an ADC in an MCU, usually. All right, my friends. So I'm having the temperature sensor getting info from the environment in the back. Please focus, right? And then, is that it? I'm just getting the temperature? No, what am I doing with it? Displaying it. So I'm spinning out some information to the environment throughout the LCD, right? Is that an embedded system, according to what you've learned in the very first lecture? What can you tell? Depends on what? What is an embedded system? According to your knowledge, I don't need the exact words. I just tell me what you've learned from it. Huh? Come again? All right. So it's a system that is bigger part of a bigger system. That's for sure. But I mean, what is it? Is it a rabbit? Is it a microphone? What is it? It's a computer, right? So it's a computer processing unit. I mean, it's some information processing unit. Does it work on its own, or does it interact with the environment? Of course, one of the premises of an embedded system is that it interacts with the environment. So basically, does this system interact with the environment? Yes, it does. Throughout the sensor and LCD. So here I'm getting some inputs, and on the LCD I'm spinning some outputs. Does it interact with real-time constraints? Can you tell from the schematic? We cannot tell from the schematic. But in your experience now, 3 weeks from the very beginning of the course, right? If you're processing some information and displaying it, are you displaying the actual right now temperature, or you're displaying the temperature from 5 days ago? What would make more sense? It's the real-time temperature that I'm trying to display, right? So most probably it's a real-time embedded system, and it is a real-time embedded system. What is your question? Yeah. It's an excellent question. I think that you've attended the first tutorial. This is why you're asking me a question. You have not attended the first tutorial? All right. A general rule of thumb is if the period is predefined and needs to be respected as a deadline, right? It is considered to be real time, even though the real time could, expand to some hours. From a human point of view, if it expands to hours or days, we're losing the sense of real time. However, according to the definition, it's still respecting some deadlines. Who amongst you have seen the first tutorial yet? Just you? I remember you from last year. Have you seen the non-real-time embedded systems in the tutorial? You don't remember? You what? No. Who amongst you attended the first tutorial? And you did not? Okay. Anyway, usually when we talk about real time, we're talking in terms of milliseconds, maximum seconds, maximum. All right? But if we want to stick to the formal definition, any period that is predefined is considered to be real time because we're respecting some kind of deadline. But in practice, you know, when you're going to go and hit the job market, if you tell someone that the computer that is in my car is a real-time system, however, the deadline is in 4 days, they're going to take you for a crazy person. All right? So usually, real-time is instantaneous, is in terms of micro milliseconds, seconds maximum. Fair enough? Where was I? Yeah. So we have here on this particular schematic a microcontroller unit, some LCD, a sensor, a temperature sensor, and we need to power everything up. What do I need the regulator for? Well, to make sure that the voltage is appropriate. A smarter unit, if I want to substitute the regulator here with a smarter unit, what would that unit be? Yeah, a power management unit, good for you. This is from last week. All right, so let's see. We're studying a case here. If we go back to the previous picture, we've seen that the name of the microcontroller is Atmega, right? It has some suffix, but I don't care about it right now. So I'm telling you, this is something that I'm giving you right now. I'm telling you that the particular microcontroller, the Atmega, it comes with a 10-bit ADC. Inside it, I can find a CPU, a memory, I/O pins, you know, I/O channels, ins and outs, and I can have one of those I/O pins is connected to an ADC. So where's the ADC now? I know that it's inside the MCU. Make sense? Everyone still following? All right. Now my question is, the temperature is a physical element, right? So it varies continuously. And usually, if you didn't know by now, I'm telling you this info, the temperature is not really measured in Celsius or Fahrenheit or whatever. It's seen by the electronic component as what? As some kind of voltage. All right? This is what I'm telling you. So the sensor sees the temperature as something, as a voltage that is varying between 0 and 5 volts. Make sense? And then, of course, there's some kind of mathematical formula. Leave it open. Leave it open. So it varies between 0 and 5, right? And then there's some mathematical formula that is used in order to transform the voltages into some, you know, a unit into some temperature in Celsius or Fahrenheit or whatever. Who amongst you have already used the temperature sensor here? No one? All right, so we're going to use it. You can use it this year. Yeah. Yeah, voltages. Yeah, electronic. In a way or another, generally speaking, yeah, they're always seen as voltages, because remember, we speak ones and zeros. All right. Now my question to you is: everyone's following till now, all right? So the physical grandeur, I don't know how to translate it in English. Let's call it element for now. So the physical signal that I'm trying to measure. It varies between 0 and 5 volts. All right? Now I want to translate it. I want to map it to some numbers. The hypothesis here is telling me I dispose of 10 bits in order to translate this continuous signal. All right? My question to you is, if I put aside the 0 volts that will correspond to the integer 0, let's say, all right? How many numbers do I dispose of in order to map whatever is coming after 0 all the way up to 5 volts, and why? So one more time, I'm trying to map the continuous 0 to 5 volts into a bunch of integer numbers, all right? And then dispose of a 10-bit ADC here, all right? So what are the numbers? The numbers, they vary between what and what? You want to go for it? Go ahead. 0 and 10,024. So 0 and 1024. Not bad, but someone can do better. Yeah. Come again? So 0 between 0 and 1023. How come? Yes. Good. So definitely you dispose of 1024 numbers to represent 0 to 5 volts. However, if we put the 0 aside, we're left with 1023. Make sense? Perfect. So it's between 0 and all the way up to 1023. Everyone is on the same page? We're all good here? All right? Have we seen something like that in the DSD course? I think I've mentioned it somewhere. I don't remember anymore. I did. All right, perfect. So this should... No, you don't remember anymore? So this should ease stuff to you. Now, this means that I have a scale, right? And each number is each value is mapped to a particular number. So the value 0 volts is mapped to what number? 0, right? It's down the scale. Now all the way up, the number 5 volts, the value 5 volts is mapped to what number? 1023. Make sense? Now in between those, there are steps. I want to know the length of my step. How can I do that? So in between the minimum value and the maximum value, I have a bunch of steps. Make sense? How do I get this particular step width or length? Doesn't really matter. All I have to do is what? Divide the 5 by 1023. All right? So I dispose of 1023 numbers. I'm going to divide them on the 5 volts that I'm trying to represent. Any number between 0 and 5. Make sense? This gives me the what? The length of the step. So the first value is 0. What is the second value? It's 4.88 millivolts. What is this third step value? 2 times 4.88, 3 times 4.88, 4, etc., etc. So this is the length of my step. And this is what we call the resolution in electronics. Are you following? Please follow up. It's important. This is the resolution. This is how sensitive I can follow up, the sensitivity level of me following up the signal. This is awesome. This is awesome if the sensor is also capable of spitting something between 0 and 5 volts. Is it the case in real life? Is it always the case in real life? Different manufacturers, different reasons, different objectives. We don't dispose of 0 to 5 volts from the side of the sensor. We have it from the ADC, but not from the side of the sensor. Why would this be problematic? Yeah? The ADC. The resolution is always ADC-wise because it takes care of translating the continuous into a sampled one. Where was I? Yeah. So why would that be problematic? Why, if the sensor is not compatible, the sensor is unable to split voltage between 0 and 5, why would that be problematic? Let's study 2 different cases. What if the sensor, and this is impossible in real life because it would be crazy if manufacturers did that. Imagine if the sensor is able to give values between 0 volts and 10 volts. What am I losing here? Half of the readings, I'm not able to follow up with them because to me everything that is after 5 volts is considered to be 5 volts to me. This is the maximum value I can see. Make sense? And this almost never happens in real life. Almost. Maybe some crazy man tried to do something, but all right. Second case study. Let's go for it. Imagine now that my sensor is unable to spit voltages beyond 3 volts. This is problematic as well. Why? I'm losing 2 volts in my representation. I have 2 extra volts that I don't even need to represent them. Plus my resolution is calibrated to the 5 volts. I'm leading you somewhere, so follow up. Everyone's following up to now? All right? So second case here is that I don't need any information beyond 3 volts, so why bother divide the resolution on the 5 volts? I can do better. I can calibrate better. With sensors that only spit information between 0 and 3, I'm only using roughly 614 of the 1023 that I dispose of. So I'm using a subset of the whole set that is defined by my ADC. Everyone's still okay with that? If you have questions, please ask them now. So till now I'm seeing I'm only using a subset. I don't want that. I want to expand that subset in order to make it cover 0 to 3 with a better resolution. As an engineer, am I able to do that? All right. Anytime I ask you as an engineer, am I able to do something? You always answer yes, because we're always able to provide some kind of solution. Not the best one, but some kind of solution. This is your job. All right. So yeah, we can improve the resolution, and this is where the AREF pin becomes handy. So everyone takes note of the thing that I just said. The AREF pin is used in order to redefine the resolution of the analog reading. Now the question is, how so? Well, all I have to do is I want to apply a reference voltage. Instead of using the default one that is 5 volts, I'm going to say that my reference voltage is 3 volts. All right? So I'm going to apply 3 volts at the AREF pin. By doing that, the ADC will know now that the maximum that I can read is 3 volts and not 5 volts anymore. Hence, it will redefine the resolution. What would be my resolution now? Instead of dividing 1023 by 5, what should I be doing? Or the other way around. What should I be doing? I'm going to use 3. All right? So I'm going to divide 3 by 1023. Why not 1024? Because my 0 is already allocated, all right? I'm putting it aside. And this will give me a step of 2.93. So more precise. This is a precision of, if you do the math, you're going to find out that it's 40% more precise than the value that I had before. What was the value of before? 4 point something, right? So yeah, a smaller step length means that it's more sensitive to the variation. Can anyone suggest another solution for to have, without using the AREF pin, to have a better resolution? Someone from the other group suggested something extremely interesting. Anyone is able to do that here? Yeah? I know you're chasing away flies. No, without touching the voltages. Yeah. Forget it. So basically, there's another solution, is to get a more sensitive sensor. However, if you want to do that, you'll pay more money for it. So it's more expensive, right? A more precise sensor. So instead of doing the resolution on the On the microcontroller side, you do it on the sensor side. Yeah. In case of 3 volts. Come again. So in case of 3 volts. All right. So in case of 3 volts, remember, the voltage that you have represents the physical signal that you're trying to follow. All right? So in case of 3 volts, your physical signal could be anything between 0 and 3 volts. Make sense? It can take any value between those two. The idea is how to map those values to some numbers on the digital side. Get it? So this is what you're trying to do. What you're trying to do here is to better the length of the step. So 1.5, this is any random value that could the temperature sensor be spitting. This, or maybe I didn't get your answer question. In case of 5 volts, all right. No, this is what I'm trying to tell you. In case of 5 volts, you're reading any value between 0 and 5 volts. It could be 2.5, it could be 1.0, it could be 0.5. This is what you're reading from the environment. All right? You're not trying to map 0 and 1s. You're trying to get a voltage into a sampled one. All right? All right, you had a question? What I'm trying to the idea that I'm trying to convey here without getting into much details is that you can either deal with it using your microcontroller and the ADC that you dispose of, or you can deal with it on the side of the sensor. And if you decide to deal with it on the side of the sensor, this means that your sensor is more advanced, hence it's more expensive. How we deal with it, leave it for later. Fair enough? Yeah. A more intelligent sensor, a more sensitive sensor. Sensitive. Leave it for later. This is not my focus here. All right. When you're gonna hit the job market for sure, you're gonna face stuff like these. You're gonna see drawings like these. In GSD, I've introduced something that is extremely relevant in the context of electronic components. What was that? What was that documentation? What do we call it? The documentation that tells you what an electronic component is supposed to do, etc. Data sheet, all right? Here, and everyone should know now, that by now, is what we call a schematic diagram. A schematic diagram of what? The example that you're seeing here is the schematic diagram of the Arduino Uno revision 3 board. So this is the schematic diagram of a whole board. It's not about the microcontroller that are on the boards. Those we're going to see them by the end of today's lecture. All right? So you will face situations where someone will gonna give you, a drawing, a schematic, and you need to decipher it in a way or another. So let's try and do that. Your intuition, can you point out on the schematic here, the big microcontroller and the small one? Go on. Okay. Tant pis. Okay. All right. This is just to give you a taste of how we do stuff in real life. Now, whenever you're going to remember this lecture and this class in general, or me, maybe years from now when you're working in this industry, let's say, right? You're not going to say, "Oh, I'm doing that. I've barbecued my microcontroller because I connected the pin as Asan told me 5 years ago. What I'm telling you is in red over there. You always refer to the data sheet. In my class, I'm giving you examples. This doesn't mean that this is the truth everywhere and every time. You need to make sure that what I'm saying, first off, is true. Second, if it's applicable to whatever component you're dealing with or whatever microcontroller you're using. All right? You always refer to the data sheet. You don't assume, unless you want to end up with, I don't know, something burned between your hands. Doesn't really matter. Alrighty. Here, it's an excerpt of the data sheet of some Atmega. Not the 16, apparently. But maybe not necessarily the one that is on the Arduino board. Maybe. Just giving examples. Let's see. How many pins do I dispose of on my Atmega 3208? 28, perfect. All I have to do is read whatever is in front of me. Make sense? This is what we do in the data sheet. We go and read stuff. Everyone should take note of the following. The Atmega, it belongs to something that, a family of microcontrollers that is called the AVR. AVR stands for Advanced Virtual RISC. So RISC should ring a bell. This is from last year, CA course. All right? Awesome. Now we were guessing, wake her up. Wake her up. We were guessing what did the 16 mean and what did the 32 mean, etc. Some of you said that it's 16 bits, etc. Let's find out. So here we're saying that the CPU is a RISC-based CPU with the word length or the width of the word is 8 bits. 8? Just read. We're just reading. All right? So the 16 and the 32 are definitely they have nothing to do with the length of the words because it's 8 bits. Who can find out what does the 32 or 16 mean? It's the memory size. The memory size. I didn't say the SRAM. We're going to get to that. Question in the back. Yeah. So I'm telling you that the operating voltage of my microcontroller, so my microcontroller, is it the whole board? Is the microcontroller the whole? No, it's just that component that we've seen on the board. I mean, it could one component on the board. I'm telling you that the operating voltage is between 1.8 and 5.5 volts. My question to you is, if I apply 10 volts to my microcontroller, what would happen to it? Barbecue. Should I ever apply high voltage to my microcontroller? Never. Fair enough. Another note, another take-home message is the program memory. Notice, I'm calling it not me, but they call it program memory. This means it's a memory dedicated for what? For the instructions. How big is it? 32. On an Atmega 16, your program memory is 16K. So whatever you're having as a suffix to the Atmega, this is one of the suffix. This is the size of your program memory. Yeah. One more time.
Word size.
Next to the CPU. It's RISC 8-bit. CPU over there, second line. Program memory. Now you CA experts. You should be experts by now. You're in your 4th year, right? Can my computer, whatever that computer is, can my computer work if I only have a program memory? What should I have in order to be having a functional computer? To deal with the data as well. So I need the data memory. All right. What is another name for the memory that we learned last year? The one that we learned last year. I'm not saying that it's the only one out there. RAM. Thank you so much. So here you can see the SRAM. This is the technology. There's SRAM and DRAM. We've talked about that last year. All right, and it's 2048 bytes. The SRAM is dedicated for data. The flash memory, which is the program memory, is dedicated for the instructions. Yeah?
Is this always the case?
Come again?
Is this always the case?
Read the thing in red. Is it always the case? No. We always refer to the data sheet. So we've seen in memory for the programs and in memory for data. And there's a third type of memory here. What is it? Are you able to identify it? The EEPROM. Have you seen something like that before? Not really. All right, so please take notes. The EEPROM is dedicated for the coder, for the user. This is where you store things that you need to save and use later on. The EEPROM is for the coders, for you programmers. You can store in it calibration references. You can store some threshold value that you're going to use in your system, etc. This is for you. This is your hiding place, where you put your data that you want to save. Let me finish. Now, I'm going to give you more info about two things. First, I need to ask you one question. According to what we learned last year, when we power off a computer, what happens to the RAM? It's volatile, so basically disappears. All right? So the RAM is volatile. The flash, it's not volatile. So basically, whenever you upload some instructions in your program memory, even after power off, the program is still there. Not the data, the program. Two different memories. We're going to get to that. What does it mean to have two different memories? What about the EEPROM? So I'm going to give you a hint. The first two letters of an EEPROM is electrically erasable. Electrically erasable. What does it mean? When I power it off, what would happen to the data, to the user data that I'm saving in there? Poof? Or they still, or they stay? On power off, they stay. However, you can erase them, and you need to apply some voltage in order to erase them. So it's controllable. You can say that I want to erase them, but however, the default thing is they're still there if I don't erase them. If you have a question, direct it to me. Question? No, you good? How many memories in my microcontroller? 3. One for instructions. Volatile or non-volatile? Non-volatile. One for the user. Volatile or non-volatile? Non-volatile. And the third one is the RAM that is, as usual, volatile. All right. Hold on. Let me finish first. The last sentence, the last line there. This is what we talked about a moment ago, right? This is your ADC. So your microcontroller has in it an ADC that is there, right? And what is the resolution? What is the number of bits that you dispose of in order to deal with the resolution? 10 bits. Wake him up. Your question. She forgot it.
Yeah, I forgot it. Does the RAM have both, like instruction and data?
What did I say about the RAM? What did I say about the RAM? Strictly data. Stating facts, not arguing with, for or against. All right, a lot of things that we're going to learn throughout this course. So to keep you on your toes, we're going to use the different channels here, those things here. We're going to learn about them. What is another name for a clock? Oscillator, because it has a hertz unit here. For those who followed last week's lecture, I said that on the Arduino board we have external clocks. However, inside the microcontroller itself we have an internal clock, and this is your internal clock. It's an oscillator. And we have a bunch of timers, etc. We're going to see those throughout this course, don't worry about it. What I need you to focus to check out right now is the packages. Now my question to randomly, I don't know, her. It doesn't really matter. I mean, you want to go for it? So what is a package? Do you have any idea what a package is? That's exactly it. Perfect. So a package is, it's like a box that you put the stuff that you want to, I don't know, send as a Christmas gift or something like that, right? Make sense? So a packaging is the format, is the shape of the IC itself. And that particular microcontroller can come in 4 different ones. I'm showing you 3 out of the 4. Which one do we find on the Arduino board? The bottom one, this one. However, for different reasons, we can have different shapes as well. One with legs, one without legs, and you have the names of them here. Of course, I'm going to ask you a question about it. Wake him up. Here, important. My question to you is, why would that be useful? The fact that I can have different packages, so different packaging formats, it's important in the context of RTES. What's RTES? In embedded systems. Why it's important? Yeah? So remember the different constraints, timing constraints, energy constraints, but what else? Size, right? So imagine that on the plane or somewhere, you don't have the space to have the big one, let's say. You cannot have a rectangle for some reason. You need a square, for instance. All right? Good. All right. So we're always referring to the data sheet, and we're going to keep on seeing the different things that could be found in a data sheet. All the things that you're seeing here, we're going to see in details later on, all right, step by step. But for the time being, I need you to see first, second element, and first element on the other side. So something that is called enhanced power on reset, the power up timer, and the baud, the brown out detect. What can you imagine those are? I'm not expecting you to know. I'm just, stimulating your curiosity. Want to go for it? Go ahead.
For example, if there is a lower voltage, it's not complete blackout.
Fancy. Anyone else? She talked about the brown out detect. I'm going to develop it a little bit more. What about the first two? Anyone has an idea? Yeah? The first one, enhanced power on reset, yeah? Okay, not really. Right. Anyone for the second one, the power up timer? Yeah. Speak up. Not really. But yeah, sure. It has some counting. Yeah, you got it right. All right, so let's start first with the enhanced power on reset. This means that whenever you're powering on the board, we're making sure that everything is reset. You go to the very beginning of everything. Why is that important in the context of my course? I mean, in the industry, generally speaking. Why it's important to make sure that whenever I'm powering on a module, a component, a board, whatever, right, I go to the very beginning. Let's try him this time. Come again? Dirty what? Data. Yeah, it has some sense in it. Anyone wants to try something else? Go ahead.
Because when we turn it on, we might want to run some checks again.
All right. The power on reset, it guarantees that I'm starting fresh. Whenever I'm powering on the controller, I'm going to go back to the very beginning, because sometimes it can go crazy for some reason, right? So to make sure that I'm going back to the very beginning, all I have to do, unplug and plug back in. Or just push the reset button. I'm going to find that later, right? So this guarantees a good behavior. This guarantees that I'm going back to the very first nominal, we call it a nominal behavior. And of course it's important. Can you imagine that you plug in, plug out, and then it remains the same? It would be crazy. Power up timer. Those, especially the ones who followed last week's lecture. Anyone? I'm going to give you a hint. My microcontroller is made out of different components. So inside it, I have different components, right? I have a board, and on the board I have a microcontroller, and inside the microcontrollers I have different components. Make sense? And I use the power up timer for that. Perfect. So the power up timer is the time. I'm going to count the time needed for the slowest component to be up and running. So I'm going to be, are you ready? Yeah, ready. Are you ready? Are you ready? Etc. I'm making sure that the slowest component, it's taking its time to be up and running. So this means that all the components are ready at the same time. This is dictated by the slowest component, whatever that component is. And last but not least, and she started answering correctly, is the brownout detect. So usually here as engineers, you need to feel something. Brown represents a color, right? What if I tell you there's something out there called a blackout? What is a blackout? What's a blackout? If a blackout it happens frequently here. Woof, no more electricity, right? So this is a blackout. This is nothing at all. A brownout is less severe from our point of view. No, I'm not going to put it this way. A brownout is not a blackout. It's not a complete loss of current. It's just a drop in the voltage. Everyone's is following? Make sense? So a brownout is not a complete loss of the voltage, but a drop in it. Why is that extremely dangerous when it comes to real-time embedded systems, to microcontrollers, etc.? Because you're messing with its behavior. Because it doesn't have the voltage enough to do what's supposed to do. All right? So if it detects it, this means that we'll be able to reset. All right. Okay, one more important thing from here. This is in the real professional life as well. Let me choose her behind the girl in red. Yeah, him. In blue. Operating temperature. Are you able to see it? So what is it? It's between what and what? Minus 40 and plus 85. I'm giving it to you. Celsius. All right? My question to you is, remember, this is a microcontroller. I've showed you the picture of a microcontroller. Imagine that my microcontroller is in a vehicle in the middle of the desert, and it's 90 degrees out there. Let's imagine, all right? What would happen to my microcontroller? Not necessarily, because I'm not messing with the voltage. So not necessarily. Of course, if you're going to fry it with the flamethrower, yeah, sure. I'm talking to him. I need him to think. So they're telling you that the operation temperature is between minus 40 and plus 85. Now it's 90 degrees. It might stop working. In another term, we cannot guarantee the behavior of it anymore. Question number 2 for everyone that is here. Let's imagine a military application. All right? What would be the temperature operation ranges of microcontrollers that are used in military systems, and why? Way wider. So instead of stopping at plus 85, let's say, it can go up to 150 or something like that. And this will cost a lot of more money, for sure. But why is it important? Well, usually the military, they need to guarantee the behavior of the systems. This is why they invest a lot of money in when it comes to the resistance of different hazards, such as temperature, etc., etc. One of the things that I had the chance and opportunity to work on are the test units of cars in Finland. So over there, usually, let's say in France, for instance, whenever you want to try your car in extreme conditions, you need to build something that we call a cold room, right? And you take your car and you test it over there in the something that is, spinning, and it's emulating in extreme weather conditions and the, driving on a road. However, in Finland, for instance, because of the temperatures over there, you can test in real life the cars and see the resistance. And what would happen if, let's say, your computer car is supposed to work in between minus 20 and plus 40, let's say, right? You can see the effect of it running on a minus 30 temperature, for instance. And this is what we call testing. And there's a whole domain of test and checking the resilience of the system. Extremely interesting. All right. One of the things that I need you to remember today, but we're going to tackle it in 2 lectures from now, is something that is called the watchdog timer. Does anyone have an idea about what's a watchdog? No one here? So, you have an idea? Shoot. A what? Hold that thought for later. Keep that in mind. We're going to see it. It's another important aspect that you're going to find in different microcontrollers and different systems out there when you're going to hit the job market. All right. Let me ask her. Are you ready for me? All right. So I've said that Atmega belongs to the AVR family. Do you remember what AVR stands for? No, over there. I'm asking her. Do you remember or not at all? No? Okay, so it's Advanced Virtual RISC. I'm telling you that we have 5 different categories out there, but I'm going to show you the 3 that I know of. This dates back from my time. So we have the tiny AVR. This is small memory, easy applications, all right? Naturally, we have the mega AVR. This, you've seen that before. So this is a good trade-off between complexity and memory size. And then we have the X mega AVR, all right? So these are for the complex applications and large memory, so a huge number of instructions. The Atmega that we've seen on the Arduino board belongs to which one? The Mega, the second one. All right, this is for your own knowledge. You can also see out there some AVR that are used in combination with application-specific approaches. So application-specific, this is closer to what? FPGAs? No, closer to ASICs. All right, so there's that. But then again, there's another family of AVRs that come with FPGAs. All right, so we have a versatile different families for the AVR. The one that you're going to see and work with this year is definitely the second one. All right? So let's check the naming convention now. So by now you know what the 16, 32, etc. It stands for what? The numbers, following the letters are what? This is the size of program memory, right? The mega is to say that to which family it belongs. And can anyone guess what is the AT here? It's a guess, wild guess. Okay, so it's the name of the company that creates the microcontroller. Okay, it's Atmel. And today it's owned by Microchip. So you might know Microchip better than Atmel. Okay? So this is the program memory size, and this is the family, so it belongs to the mega. Okay. So what's so special about AVR? Why did I take it as an example in my course? So remember AVR, one example of the AVR is the Atmega, and the Atmega is on the Arduino boards. So why did I choose it in my course? You can go and buy an Arduino anywhere. Make sense? So you have access to that particular one. It's relatively easy to use. But I'm going to talk about the attributes. I'm trying to talk about the attributes. Yeah. If it's RISC, so definitely it's general purpose because it's a RISC, remember? Architecture. Okay, I'm going to give it to you. This is me giving you a new piece of information. Most of the instructions that are available to you for use are executed in a single cycle. Single cycle, this is, remember, CA. Why is that good? What? Use performance, good. Definitely, because remember, the performance equation, do you still remember it? Roughly? Huh? Speak up, please. Yeah, definitely. So performance is 1 over execution time. So execution time, do you still remember the equation to get the execution time? The frequency is there for sure, but what else? Number of instructions and how many cycles does an instruction take? Right? So I'm telling you, all instructions, they take only 1 cycle. So you can think that you can really estimate how much time will it take to execute a program, because if you know the number of instructions, all you have to do is get the frequency, and that's it. So this is perfect. Yeah? Not all the time. You can have different cycles within the instructions. So an instruction could take more than 1 cycle. But not here. Here it's 1. And. So the first one is helpful for what in the context of embedded systems? So in the context of RTES, execution time, so deadline, etc. The second thing that is extremely important is, I'm giving you this other piece of information is, we have different power saving modes. Why is that extremely important in the context of embedded systems? Energy consumption, so hence I don't have unlimited energy. So it's a good thing. So this is why we say that microcontrollers and AVRs, etc., are the heart of embedded systems, especially the easy do-it-yourself embedded systems. And when you change the application domain, you need better microcontrollers or even CPUs. And it's relatively small as a word size. Oh, by the way, it's a RISC. What is the other? ISA category, yeah. CISC. Yeah.
Are there like pros and cons to like small word size?
There will always be cons and pros. It depends on the thing. Huh?
What are the cons and the pros of the small word?
You tell me. If I'm giving you 8 bits to represent some number, is it enough for extremely big numbers? One more time. I'm not saying for this particular application. In general, if you have only a limited small number of bits to represent a number, are you able to represent big numbers? No. So you can see it depends on the engineering work is always about having trade-offs and understanding the case that you're trying to study. Get it? There will always be positive and negative things. All right. So let me choose this guy over there. Yeah, you. Yeah. So let's try and see what's happening here. So can you go ahead and try and figure it out? It seems, come on. So your stupid boss, and this is what happens sometimes in real life, he comes to your office and he gives you a documentation of 100,000 pages, and he's like, deal with it by the end of the day, right? So the first thing that you're trying to decipher here, this particular schematic, what's happening? What are you seeing here? Use your experience. Huh? Come here. Oh, awesome. So you identify inputs. Can you see what's inside the inputs here a little bit? This looks like what? They look like what? Things from, try to remember the things that we've seen in CA. Is it memory? Does it look like a memory? Definitely not, because first off, you called it input, so it's an input. Second of all, you can see R0, R1, R2. These are registers. So we have a bunch of input registers here. Make sense? What is the length of my inputs, by the way? So it's R0 all the way up to R7. How come? Why? Why is it 8? Remember. You don't remember? We just said it. What is the word size at mega? Huh? It's 8. So basically it makes sense. So I'm getting 2 inputs here. Hold on. Getting 2 inputs. I'm doing what? What am I doing in the orange part? It's more ORing, but fine. I'm doing some kind of operation. It's ORing. It's normal. And then, what am I spinning out? The output. How long is the output? 8 as well. Why? Because Atmega speaks in terms of 8 bits. Now my question to you, according to the things that you've learned today, how many cycles does the whole thing here take? So it's an instruction, huh? I'm ORing an input with an input and putting it in an output. Huh? Yeah, definitely. What I'm using here is AVR. 1 cycle, perfect, man. So all this is done in only 1 cycle. All right? Yeah. Coming in, all in 1 cycle. Instantaneous. You have your inputs, you read them, you operate on them, you spit it out, all in 1 cycle. Your question?
The register size on the previous slide 1 bit?
Coming in, is the register size on the previous slide what?
1 bit. So like every register holds 1 bit?
Yeah, definitely. Yes, definitely. No, it is there. I mean, the R0s, etc., is considered to be only 1 for the summing. We're going to see it throughout the lecture. No worry. All right. So this is what we've learned to now, and this is just some, Always refer to the data sheet. They will tell you how many general purpose registers do you have, which one are used as inputs, if you can use them as inputs and outputs, etc., etc. It doesn't really matter. The idea here is everything's happening in 1 cycle. My question to you is, how many instructions per second can I execute when I'm using an AVR if my frequency is 1 megahertz, and why? So my clock is 1 megahertz, all right? And I'm trying to find how many instructions I can execute per 1 second. How many cycles per instruction? 1, right? And I have 1 megahertz, so that's 1 to the power 10 to the power of 6. So how many instructions can I execute in a second? 1 times 10 to the power of 6. In 1 second. 1 to the power of 1 times 10 to the power of 6 instructions per second. That's relatively fast, no? 1 million, yeah? Alright, so this is the last part we'll be seeing together, because this is where I almost stopped with the first group. Now I need someone who is confident enough, who believe in themselves. No one here? Come on. You in the back. Are you confident enough? It's okay. We're going to build that confidence together. Let me try something. Check this out. Are you able to see anything here at all? Here. Anything? No, I can't. I honestly can't. Anything that you can see. Can't you see anything? Here, for instance, can you read anything here? AVR CPU. Here we have the name flash, and here we have the name SRAM. Can you remember the flash is for what and the SRAM is for what? Shh, guy in the back. You can't? Who can help out? Yeah. I'm not saying big or small, I'm saying they're used for what? Yeah. One more time. For the? I honestly can't hear you. No. Yes. So SRAM, you got it? So SRAM, we said it's for the data, and the flash is for the program, for the instructions. Now, back to the future. No, back to the CA course. When I have separate memories, let me zoom in, it's better. Now I can zoom in. Now I have separate memories, one for the program and one for the data. And then I have my CPU here that is connected to both memories, right? What do I call this microarchitecture? Harvard. Awesome. What is the other one that we've seen last year? And what's the difference between the two? So in von Neumann we have one physical memory for both data and instructions, and in Harvard we have separate one for data and instructions. And here it's definitely a Harvard memory. Can anyone feel why we have a Harvard memory here? Just a feeling. What a feel. Anyone? No? Efficient, what do you mean efficiency? I'm not expecting you to know, I just want to sense your feeling. So this means what? So yeah, speed, of course I care about the speed of execution. Why separate the memories? You want to try? Go ahead. Huh? There's something related to pipelining. I will take that. Good for you. Did you add something? Come again? You need to shout. Avoid data hazards. Avoid data hazards. No, why? Why would you avoid data hazards here? No, it doesn't really matter if we're talking about the same memory or not, remember, because usually your hazards, you got them from the registers, remember? Sorry? I don't know, check the data sheet. Yeah. Not necessarily. Yeah? Go ahead. I swear I can't hear. I swear. Yeah. There's no operating system? Operating system? Not talking about software here. Not mentioning software anywhere. We're going to find out that you're going to run an operating system on it together this year. All right, I'm stopping here for that. This is the Harvard. One last thing that I need to show you before you leave. This is what, just keep it for 3 minutes, that's it. All right, we're going to try to decipher this. This is what you see in the data sheet. All right, this shows the whole insides of a microcontroller. So you're going to identify the different elements. I'm so tired now. Can you see the EEPROM? Anyone can see the EEPROM? Who can see it by raise of hands here? Yeah, good. You have good eyes. So the EEPROM is here. All right? Shh, I'm not done yet. Here you can identify what? The oscillator. Please take notes. You can notice that the oscillator, aka the internal clock, is connected throughout something to the external world, to the other modules on a board, for instance. Anyone can guess what do we connect the internal oscillator to? Can you guess? Go ahead. To the what? No, to the what? We connect it to what? What is that other system? No, where? You said external clock? Yes, correct. Usually to keep everything synchronized, right? We can connect the internal oscillator to the external clock on a board. We can do that, and this is what we do. My question to you, why bother having an internal clock if we have an external one? No. Yeah. Well, if you have an external one, it's extremely easy because we can connect to it. But remember, the microcontroller does not always come in a board. You can buy it on its own. So it has its own clock, so it can function even though you don't connect it to an external board. Okay? I'm not done yet. Can you locate the AREF pin? AREF, it's outside. Remember, we've seen it. So it's not those. It's definitely not VCC and definitely not ground. There's something here. Maybe we'll talk about it later, maybe. And there's the AREF. It's physically connected to what? Can anyone read? To MUX and ADC. So it's physically connected to the ADC. Hence, I didn't lie to you. Can anyone locate the ins and outs? Here and here, here and here, right? This is the last thing that you're taking note of. We call those pins the ports. Ports, as in port. Okay? So the inputs and outputs are called ports. One last thing. Here we have the flash and the SRAM. It's connected to, maybe I have a zoom. Yes, perfect. So yeah, I have the program flash and the SRAM. What can you notice about those two here? Program counter connected to program flash, makes sense. Why? Because the PC is used to know which instruction I'm going to execute next. What about the stack pointer? Does it ring a bell? What do you use stack pointers for? This is from last year. For the functions or the procedures. So hence it's connected to the data. Anyone can see the CPU here? In order to locate the CPU, we need to locate the ALU, which is the heart of the CPU. So basically this should be the CPU with the program counter here. And we're going to see the different registers next time. All right, thanks for coming. See you soon.